We think of the sun as light and heat, but sometimes it becomes a radio noise generator so intense it can drown out technology. Not by hacking anything, not by breaking satellites, by overpowering receivers with pure static. Tonight's case: solar radio bursts, the moments the sun effectively screams across the spectrum. A solar radio burst is a sudden spike in radio emission associated with solar activity. To a receiver, it looks like the background noise level jumped instantly. If the noise rises enough, weak signals become unreadable. The system doesn't fail mechanically, it fails to separate signal from noise. Two different space weather effects get confused. HF, radio blackouts, often come from ionospheric absorption during flares, while radio bursts can directly jam receivers by flooding them with solar noise. Sometimes both occur near the same time, which makes diagnosis messy. But the physics is different, and so are the symptoms. A key fingerprint is geometry. Impacts are typically strongest where the sun is above the horizon. The day side is exposed, your antenna is literally pointed into the noise source. The night side is shielded by the planet. That's why a global outage report often has a clean boundary when you map it. The core failure mode is receiver overload. The burst raises the noise floor and can push front-end stages toward saturation. Even without full saturation, signal-to-noise collapses and tracking loops lose lock. In GNSS terms, CN0 drops and the receiver can't maintain correlation. It's an engineering problem triggered by a solar event. December 2006 delivered one of the clearest demonstrations. Intense solar radio bursts were measurable in GPS receivers and produced real tracking degradation. Studies describe significant effects during the strongest event on the 6th of December 2006, including loss of lock behavior in some conditions. That's not a rumor, that's instrumented evidence. Solar radio intensity is often described in solar flux units, SFU, so engineers can quantify how bad an event is. Extreme bursts can reach extraordinary flux levels at microwave and L-band adjacent frequencies. The point isn't the number, it's that the sun can temporarily dominate the radio environment near Earth. When it does, receivers are the battlefield. GNSS signals arrive at Earth extremely weak, so receivers rely on processing gain and stable tracking loops. A strong burst injects extra noise right inside the band where GNSS listens. That can reduce SNR, increase slips, and in severe cases cause lock loss. The effect depends on frequency, polarization, antenna pattern, and receiver design. Solar bursts aren't just historical. Research on the 6th of September 2017 events reports GNSS interference during intense radio bursts associated with major flares, including measurable SNR impacts at multiple GNSS frequencies. Different bands can show different vulnerability in the same event. That variability is why engineers treat SRBs as a real operational risk, not a trivia fact. Solar radio bursts are classified by spectrogram signatures, types 2, 3, IV, each hinting at different physical processes like shocks or electron beams. You don't need the full taxonomy to understand the threat. Different burst types can occupy different bands and durations. Translation: some bursts are brief punches, others are long blankets of noise. And duration is what kills tracking. HF disruptions often come from ionospheric absorption during flares, a different mechanism from direct burst noise. That's why HF can die even when GNSS is fine, and GNSS can degrade even when HF reports are inconsistent. Same sun, different layers, different physics. If you don't separate these, every space weather story turns into confusion. Radar can also suffer when background noise rises, because it needs to detect weak returns. A burst doesn't have to turn radar off to be dangerous. Reduced detection range, degraded tracking, and increased uncertainty can all follow from a worse SNR environment. It's the same equation everywhere. Signal to noise decides reality. Bursts are monitored with spectrographs and solar radio telescopes that record intensity versus frequency and time. This isn't guesswork. You can see the burst as a structured event in the data. Standards and reports describe how these sensor systems collect and process solar radio emissions for space weather monitoring. Measurement converts "the sun screamed" into a plotted, time-stamped hazard. You can't prevent a burst, but you can design resilience, better filtering, robust front ends, smarter tracking loops, and operational procedures when alerts fire. For GNSS, multi-frequency and better interference handling can help, though extreme bursts can still exceed margins. The goal is graceful degradation, not invincibility. Engineering buys time against a star. Forecasting impacts is hard because it depends on burst intensity, bandwidth, beaming, and the specific receiver being used. Two similar-looking solar events can produce very different radio consequences at Earth. That uncertainty is why space weather is not only astronomy, it's risk engineering. If you operate critical systems, you plan for what you can't perfectly predict. GNSS isn't only navigation, it's timing for systems people rarely associate with satellites. When tracking degrades, timing stability can wobble, and the effects can look like ordinary technical noise. That's why solar radio bursts are dangerous. They can imitate routine interference while being planetary in scale. The real threat is silent, until it isn't. Solar radio bursts prove a simple point: Earth lives inside a star's radio environment. Most days, it's quiet enough to ignore, but extreme events can overwhelm receivers and expose how thin our margins are. Not paranormal, just physics at scale. If it sounds impossible, we investigate it.